All right, guys, we're going to finish up Life on the Edge Investigation Part 3. But we started this before Thanksgiving break, so we're going to take a minute to recap and review what we've been talking about in this investigation. So this investigation, Life on the Edge, is talking about the valence electrons. To refresh your memory, first I give you guys this handout here that you see up on the right-hand side, where you guys had to fill in with the pictures of the different elements that were missing and how their electrons were organized. And then in part 1, we used that and the periodic table in order to answer those questions. So we discovered a few things as we were answering the questions. First thing, if you remember that the row number, right? So row 1, 2, 3, 4, that's how many shells or rings of electrons an atom will have. So everybody in row 1, right, has one ring or one shell. Everybody in row 2 has 2 shells. Everybody in row 3 has 3 shells. Everybody in row 4 has 4 shells. And so on and so on. And we also learned, right, that the group A number, okay, so that group A number on the top of your periodic table is going to tell you the number of valence electrons. So we saw that everybody in group 1 or column 1 had 1 valence electron, just like everybody in group 6 here had 6 valence electrons. So that was some of the information that we learned about in part 1. All right, so then in part 2, we were talking about the electron shells and how they correlate with the Coulombic attraction that we talked about before. And remember, Coulombic attraction is the attraction between the protons and the electrons, because remember, Coulombic attraction is an attraction of oppositely charged particles. So we're going to see how this attraction of protons and electrons are going to affect all of the actually, every behavior that the atom has is going to be a result of the attraction between the protons and the electrons. So in part 2, we were comparing different elements in the same column versus the same row. And so, for example, in number 1, okay, we were comparing hydrogen's shell model with potassium's shell model. And if you remember hydrogen, he's got just one ring with his valence electron, and potassium has 4 rings with its valence electron. And so, we can see that the distance between the nucleus, the positive protons in the nucleus, and that valence electron on the outside is super small for hydrogen and a lot larger for potassium. So we said that hydrogen, right, is going to have the more attraction, and potassium, so hydrogen, more attraction, and potassium is going to have less attraction. All right, so one of the reasons or determining factors for Coulombic attraction we found out was the distance between the protons and the valence electrons. Now the other factor for Coulombic attraction was, remember, the number of protons. And so in number 2 here, we were comparing potassium's shell model with krypton's shell model. And if you remember, potassium, again, has got 4 rings, but he's only got 1 electron. All right, potassium's got 19, let me do it in a different color, 19 protons, right, versus krypton, who's got, again, 4 rings, okay, and he's got 8 valence electrons, okay, but krypton has 36 protons, right? And so we said the more protons, okay, the stronger the attraction. It's like having more magnets or bigger magnets in your center. You're going to have more pull, okay? So between potassium and krypton, potassium is going to have more attraction because it's got more protons, right? And distance doesn't play a factor because they're both having 4 shells, so they're still about the same distance away from the valence electrons and the nucleus. Okay, so we need to keep that Coulombic attraction in mind when we are doing part 3. So let's take a look at part 3. All right, part 3 says when multiple electrons are present, Some are easier, that means they require less energy, to remove from the atoms than others. The graph below provides information about the amount of energy required to remove the highest energy electron in the valence shell, which is the outermost shell. Okay, so basically it's saying if you've got more than one electron, all right, the electrons are going to require certain amounts of energy in order to take it away from an atom. And that energy is what we call ionization energy. We've talked about it before. You're going to see it tonight in your video notes. Ionization energy is the amount of energy required to remove an electron. Okay, so we're going to use the graph and we're going to use a periodic table to answer the questions. So you should have this activity paper on hand so you guys can see the graph a little better than up here on screen. And you should have a periodic table with you. So we're going to take a look and see and answer these questions together. So the first question is, what is the trend for ionization energy as you move across a period on the periodic table? And what is the trend as you move down a group? All right, so to figure out across a trend, you have to figure out what atomic numbers we need to investigate. Okay, so let's take a look at the periodic table. So on the periodic table, if we are talking about figuring out going across a group, that means, from 1 to 2 or from 3 over to 10, right? So going across the third row would be from number 11 to number 18. So we're going to take a look at those points on the graph here and to see what's happening. So all these dots represent the atomic numbers. So the first dot's 1, the second, this first dot's 1, the second dot's 2, this dot's 3, right? So what happens as you go from atomic number 1 to atomic number 2? All right, and then our next row is from 3 to 10. Well, that's from this dot to this dot. And then the next row is from 11 to 18. There you go. And then we've got from 19 to 36. In all of these, we can see that as you go across a period, okay, the ionization energy is going to increase. It goes up. Okay, so ionization energy increases as you go across a period on the periodic table. Now, as you go down a group, you have to take a look and see, okay, what numbers should I look at going down a group? Well, let's just do the first group, for example, right? So that would be looking at dots 1, 3, 11, and 19. Okay, so here they are, 1, 3, 11, and 19. What happens? Well, it goes down. So down a group, the ionization energy decreases. Okay. Ionization energy decreases. All right, let's take a look at the second question. So the second question asks, in which region of the periodic table are the ionization energies the largest? Well, we just said as you go across the periodic table, you're going to increase in ionization energy. So if you look at your periodic table, the largest is going to be in that top right-hand corner. Okay? Because as you go across, you increase ionization energy. Now the smallest is going to be in that bottom left. Right? Because as you go towards the bottom, all right, as you go down, it decreases. So bottom left is going to be the smallest ionization energy. Okay, so now we got to figure out why, right? Because all of science, the whole purpose of science is to figure out why and how things work. So why is the top right the most attractive? Why is the bottom left? Why does the top right have the most energy, and why does the bottom right have the least energy? Well, we can use our knowledge of Coulombic attraction to explain, right? So for number 3, it says, use Coulombic attraction to explain why the elements found towards the far right of a row on the periodic table have high ionization energies. All right, well, let's think about it. As you go across a period, okay, like we've seen, it's the number of protons is going to increase. All right, so number of protons, P plus is protons. Number of protons increases as you go across. If the number of protons increases, that means your attraction increases. So attraction increases. And if your attraction increases, think about it. If you've got two magnets, they're attracted to each other, and they're big magnets, strong attraction, is it going to take a lot of energy, okay, a strong pull, or just a little pull to pull them apart, right? It's going to take a strong pull. So it's going to take more energy in order to break them apart. Okay, so it takes more energy to remove. All right, so that's why we know that from the Coulombic attraction knowledge, as you go across the periodic table, the number of protons increases. If you increase the number of protons, you're going to increase your attraction on the electrons. If you increase your attraction on electrons, that means it's going to take a lot more energy to remove those electrons if you're trying to pull them apart. Just like two big, strong magnets. It can take a lot more energy to pull them apart. Now going down a row, let's take a look at number 4. Using Coulombic attraction, explain why the elements towards the bottom of a column have low ionization energies. Well, what do we know about Coulombic attraction as you go down a group? Right? The distance between protons and electrons increases, and that's the biggest factor, right? So distance increases. Right? And we said, and it makes sense, if the distance increases, think about my two magnets, right? The distance increases, the farther away the one magnet is, it's not going to be attracted, right? So attraction decreases. Attraction decreases. And so, if you don't have much attraction, is it going to be hard to pull apart? No. It's going to require less energy to remove, okay? So it takes less energy to remove an electron. Takes less energy. Okay? So that's the idea about why the elements on that right-hand side are going to be have a lot greater ionization energy than the ones on the left-hand side, because we're going to increase the attraction between protons and electrons, and that's going to require more energy to take apart an electron. Versus going down a group, now we're making more and more and more shells, more and more rings. We're increasing the distance, and that if you increase the distance between protons and electrons, your attraction decreases, just like magnets. If it decreases, then you're going to take a lot less energy to pull that electron off. Okay. All right, so let's take a look at number 5. If a large amount of energy is needed to remove an electron from an atom, the arrangement of electrons in that atom is considered to be especially stable. Thus, a high ionization energy means that a lot of energy must be supplied to remove an electron from an atom, and the electron arrangement in that atom is especially stable. Any element that has a larger ionization energy than its neighbors is going to have a more stable electron arrangement than its neighbors. Okay, so let's keep that in mind as we take a look at 5a, b, and c. 5a says which element in the first period, atomic numbers 1 and 2, has the most stable arrangement of electrons. So if you look at your periodic table, hydrogen is number 1, helium is number 2. Which one has the higher ionization energy? Should have said helium, right? Because it increases going across. So helium has a higher ionization energy, so that means helium is going to have a more stable electron arrangement. Now if we use that same knowledge for the third period, the third row there, okay, that's sodium to whatever number 18 is. Argon, thank you. It is, again, we've got sodium on the left, argon on the right. Okay, which one has higher ionization energy? Okay, well, it increases going across, so that means argon must have the highest ionization energy. So argon then has a more stable electron arrangement. Okay, so if we know that in those last two examples, right, the ones on the right-hand side were the ones that are most stable, well, are the metals on the right or are the non-metals on the right? Because that goes along with C. In general, do metals or non-metals have a more stable arrangement of electrons? All right, so if you remember that staircase, everything on the left of the staircase is a metal, everything on the right of the staircase is a non-metal. So if the ionization energy increases going across, the stability of the electrons increases going across, then it's going to be those non-metals that are going to have the most stable electron configuration. All right, let's take a look at the next question. Okay, so we've looked at ionization energy. That's an important characteristic of atoms because that's going to, one of the characteristics of atoms that's going to help us figure out how they're going to behave. Next class, we're going to see that atoms can come together to make bonds. And so what kind of bonds they make, how they behave in those bonds is going to depend on ionization energy. And it also depends on this second concept called electronegativity. So electronegativity is the ability for an atom to attract electrons to itself. So it's like the greediness for electrons. High electronegativity means that those atoms attract electrons to themselves. Low electronegativity means it could care less about its atoms. It could care less about its electrons, and it doesn't have a strong attraction. Okay, so we're going to take a look at the graph again. So take a look at the graph on your papers, and then also your periodic table. Okay, so we need to take a look and see the trends for electronegativity. So just like we did for the last graph, what we're going to do is take a look at the points and see what happens going across and what happens going down. Now, I do want to kind of warn you, please ignore these noble gases on the bottom, okay, because that's going to kind of confuse you. Those are kind of, they don't really have an electronegativity value because their valence shells are full, so we're going to ignore them. So when we go across, all right, we're going to take a look, like for example, we're going to go from atomic number 3 over to number 9. Okay, so on your periodic table, going across the first or the second column, or the second row, I should say, from 3 to 9, we get that trend. Okay, and then from 11 to 17, we get that trend, and then from 19 to 35, we get that trend. And as we can see, as you go across all of them, it increases. Okay, electronegativity increases. Now going down, again, we're going to do the same thing like we did last time. Let's look at numbers 1, 3, and so here 1, 3, 11, and 19. If you see, boom, okay, it goes down. Or we can take a look at 9, 17, and 35. Again, it goes down. So as you go down a group, the electronegativity is going to decrease. So compare this trend going across increases, going down decreases, to what we saw in question number 1, what trend we saw in ionization energy. What do you guys notice about the two trends? Okay, you should notice that they're exactly the same. As you go across, it increases. As you go down, it decreases. So that means that electronegativity and ionization energy are related. Okay, they are the same. So let's figure out why. 6b says if an atom has high electronegativity, a very strong attraction for electrons, Will it require a high or low amount of energy to take away its electrons? Well, think about it. If it's very strong, like a big, huge magnet, is a big, huge magnet going to require a strong pull or a weak pull? Okay, should require a stronger pull, right? And so you're gonna have to put in more energy to take away its electron. So that's why high electronegativity relates to high ionization energy. Strong attraction for electrons means that you have to include or input more energy in order to take away that electron. Now, the same idea for C. If an atom has low electronegativity, a very weak attraction, so we got weak magnets, all right? So everybody's had those that, just fall off your refrigerator. Those are super weak magnets, right? They just kind of fall down, all right? Do those require a lot of energy to take off your fridge? Nope, okay? They don't. So low electronegativity requires less energy to take those electrons away. All right, so again, looking at your periodic table, is it the metal atoms or the non-metal atoms that have high electronegativity? Okay, you should have said, again, non-metal atoms. They have the highest electronegativity, okay? Because we know from the trend that it increases going across, okay? And from actually, we're going to talk about Coulombic attraction in number 7. So it says, use Coulombic attraction to explain why the elements found towards the far right, those are our nonmetals, on the periodic table have high electronegativity values. Well, remember what we said last time, as you go across, you increase the number of protons, right? So we increase number of protons as you go across, right? Which, if you increase your protons, you increase attraction. All right? And electronegativity is attraction for electrons. So we increase the number of protons, we increase the attraction. That's why going from left to right, we're going to have higher electronegativity values. Now, number 8 says use Coulombic attraction to explain why towards the bottom we have low electronegativities. Well, remember, what's the big factor going down a group in Coulombic attraction? It's the distance between the protons and the electrons, right? As you go down a group, you're increasing distance. If you increase the distance between protons and electrons, just like magnets, you're going to decrease the attraction. Okay, so distance increases going down, right? And so you're going to have a weaker attraction. Okay, it's simple kind of, logic in that sense. All right, so think of atoms and protons and electrons as magnets. They are not magnets, but think of them like magnets. They behave kind of in the same manner with this Coulombic attraction. You increase the magnets, distance from each other, and you're not going to have a very strong pull. All right, last one. In number 9, it says in future lessons, aka next class, all right, we're going to learn that atoms can come together to make bonds and that the interactions of the atom's valence electrons are responsible for bonding. So let's kind of tie that into what we're going to see next class. It says looking at the ionization energy and electronegativity of metal atoms, okay, so remember, what is the ionization energy and electronegativity of metals? Low. All right, we said it's low on that left-hand side. Do you think they'll lose their valence electrons or be able to take away other atoms' valence electrons? Well, if they got low energy to take away an electron and they have very low attraction, what do you think? They're going to lose, or they're going to have enough strength to go get somebody else's electrons? Absolutely, they're going to lose. Okay, so we're going to see next class that metal atoms are losers. Now in 9b, looking at, again, the ionization energy and the electronegativity of nonmetals, remember we said that those guys are high, those guys are on the right side. Do you think they're going to lose their valence electrons or take other valence electrons away? Well, having high ionization energy means that it takes a lot of energy to take away the electron. So they're not going to lose them very quickly. All right, it's going to take a lot of strength. And because they have high electronegativity or high attraction for electrons, they're totally going to be like greedy and like trying to go out there and steal other atoms' electrons. So nonmetals are going to be the takers. Okay, so they're going to take those valence electrons. All right, so we're going to see that next class. But this class, for the remainder of class, what you guys are going to do is you guys are going to be working on periodic table trends activity, where you're going to analyze graphs just like you saw. The two ones, above, like electronegativity and the ionization energy. And you're going to figure out the trend going across and down the periodic table. So please use your periodic table and use the same thinking that we did in this video, okay, to figure out going across and down. And then you're going to be applying that knowledge in, given, two atoms, which one's bigger? Given two atoms, which one is less electronegative? Given two atoms, which one has more ionization energy? So you're going to be A, discovering periodic table trends, and B, applying those periodic table trends. Okay? So this is the end of this video, and you guys are going to take a look and work on that periodic table trends video. Please make sure you look at the homework board for the homework, because it's very important. You take the notes, finish it. There's a CER at the end of that periodic table trends that you want to do for practice, because you're going to be turning in another one next week. We'll see you next class.